Hi, okay, so this is the third in the series of the, uh, um, uh, what is it? Booting microwatt verilator simulation of the Linux kernel. Yes, okay, all right. So it's quite complex to put together what exactly what's going on here. I've compiled up microwatt VHDL uh, under verilator, so it's not thingy. So it's a pure C++ verilator application. I've then modified, enhanced the verilator C++ to do block RAM, to emulate block RAM, which I've set to 512 megabytes, and then through a mini chain loader actually got it to run with the serial console, and have now got the device tree file, the device file set to set the correct clock frequency on the serial console, and also um, set the CPU clock frequency to 50,000 here as well. So that's now why the TTYS 0 or serial 0 is now operating correctly rather than at the early boot. So um, so these messages here are from the microwatt-verilator.cpp, which I put. So I've specified the early boot mini bootloader as the first parameter, and then I've got a horrible hack which notes that the second file is loaded into the simulated block RAM at address 0x6000. These messages are by the that early bootloader, which reads the syscon syscon. Actually, if I can show that, where are we? Push D dot C microwatt syscon dot VHDL. Okay, so this is the VHDL for syscon, which has these addresses here. So these are register addresses, and those are what are being read. So that SOC signature is that SOC signature address there, right, which shows the infinite thing, and then it's decoding it, the SOC features. It's showing it's got a UART and it's got block RAM. UART 0. It also, there's a bit further down, it says whether it's a 16550, I think, or something like that. I've also added an extra parameter to the syscon, which says the boot address. So that boot address matches with 0x6000. So, and this mini bootloader will go, oh, I don't have SPI, I don't have DRAM, and you've told me that after in that syscon read over the wish bus, the microwatt .v microwatt HDL knows to tell this program SDRAM in it that it should start from that address, and off it goes. So now, to save a vast amount of time, I switched off compression. So this I had to re-enable config _kernel install uncompressed, which here %14, config _kernel uncompressed, and git push to git diff. You can see this is the diffs I had to the PowerPC boot make file. I had to add this so that it would actually the compression scripts, the preparation scripts would actually know not to run any compression. Those are the basic things, yeah, and also added to the kconfig for PowerPC, add the option to have kernel uncompressed, and this saved basically an hour of time in simulation time, of not having to not needing to uncompress. I mean, the amount of CPU time it's like 10,000 times slower. So we're up to 4 seconds here, 3.6 seconds of simulation time, and that's been running for about an hour. So it is quite ridiculously slow. 3.61 seconds there. Let's have a look over here on this one. We can see that it's going to be starting to run syslog-d, etc., later. Right. Anyway, so let's do some highlights. Here. One of the important things was that I got the early bootloader to do the initialization of the console. So that's what is running here, udebug. I had a bit of a problem with that earlier, so so this is why I put in that bootloader. But strictly speaking, it should be the Linux kernel should be initializing udebug correctly itself, but for some reason it hasn't been. So just by running this mini BIOS loader, at least I was able to get up and running and started. This was the point earlier at which in an earlier video it was saying found legacy serial port for 0. This is where it's taking over from udebug. It's going to actually transfer over to serial 0, which is in the device tree file here, %7, which is interrupt controller serial to 2000. Yes, here, that's the one, NS1650, and that you can see that clock speed of 50,000 is picked up from here, and consequently it gets there's a proper speed match between this and the uart verilog.c back under verilator. Where previously, because there was a mismatch, that was being set to 100 megahertz, and preset to 100 megahertz, but the mismatch was causing the serial clock to run at twice the speed, and the verilator simulator couldn't handle that. Couldn't adapt it. It specifically can cope with a hard-coded thing of 50 megahertz. Anyway, these are all absolutely fine. We've got, it's reporting the correct Dcache size, real block size, etc. All of these features are listed here in the device tree file. Dcache block size of 64. Yep, there we go. iCache block size of 64. That's brilliant. Firmware features, blah blah blah. MMU features. But it's actually running the NMMU. By about this point, it's set up the 2 pages. Where is it? Relics pages. Yeah, here we go. It's set up the Relics MMU, and set up just two large pages with sections with 2 megabyte pages. One executable for the Linux kernel at the very beginning, where the Linux kernel has been copied over, and 0x6.0.0 to the end of the 512 megabyte is read and write non-executable. So it starts off. So next thing, here's where it finds that serial port and tries to reinitialize it. Further down, it then takes over. There we go. The console TTYS0 is disabled, and it takes over for the. There we go. Boot console udebug 0 disabled. Brilliant. Not sure. Does it say? Oh, TTYS0 enabled. Phew, brilliant. Okay, that's good. and I'm not sure why the rest of this is a thing. Light ETH that shouldn't be in here, and it's taken up a huge amount of time. It's been about 1, 2, 3 more same thing. Networking has taken a good couple of seconds of the simulated time, but now we're at the point where it's actually running /init as an init process. Now I should be able to show you the memory running. Yes, it's still running. Tail -fbram.dump. Whoa! Let's see if we can spot any ASCII strings in this to see what it might be doing. So this is live running, spotting the memory dumping. Oh look, C out 0, no, I think no, I thought it was something significant. Yeah, this is only what's spotting the block RAM, so of what the block RAM is doing. Data in, data out. So that's D in is a write, and D in is a write, and D out is a read, because it's the out and the in is from the perspective of the block RAM. I'm just hunting to sift through this to see if there's any sign of any kind of ASCII strings which would tell us what it's doing and give us some kind of is there anything there? Any kind of expectations or any kind of hints? Yeah. No. It's not looking like actual code though, is it? Quite fascinating and well everything. Ooh, BRAM not equals. Ooh. Ooh. Ah, that's. Oh no, that's a debug message from verilator. I've got a timing of one with on the read and writes. The report BRAM not equals. There's a off by one cycle in there. It's harmless, but it's just reporting stuff unnecessarily there. As you can see, this is basically doing live memory tracing of the simulation, of the verilator simulation, which it would be extremely useful. Is extremely useful, but it's a horrendous amount of horrendously long debug files. That's not really producing anything useful. I would just have to. I'm going to stop this and leave it to get on with it, and hopefully within the next 1, 2, 3, whatever hours, we will actually get a boot prompt. This is what we're expecting to see next. We're expecting to see. This is Schenke's work. He booted this on an RTA 7. We're expecting to see starting syslog-d, starting klog-d, running syscontrol, and then finally, within some mini 3 hours later, we're expecting to see a welcome to buildroot login. But yeah, okay, I'll leave that to it. Thank you very much.